Thank you. I'm feeling like I should have just put cartoons into this one now. Maybe that's what's missing. But today I'm going to be telling you about some of the research that we do at Warwick and how we are using ultrasound to solve problems. I'm part of the ultrasound group, and there are quite a few of us, and we like thinking about the applications of ultrasound, how we can use it to make things better for people. And we like working together to solve all of these problems. Now, ultrasound, very high frequency sound waves, so this is a pitch that is so high that most of us can't hear ultrasound, so 20 kilohertz upwards is what we're working with. And it's the sort of frequencies that bats and dolphins and things like that can hear, and very young people can hear just about the edge of it. Now, when I say I'm from the ultrasound group, pretty much everyone thinks this is what I do. This is Karis, who's my oldest, giving me a right kicking. For some reason, the sonographers really liked it when there were pictures of me getting kicked with both of them. So that's what we've got as nice mementos. But when you do ultrasound, you have to have one of these to show to people, because that's what everyone knows. That's not what we do. So I thought I would turn this into a little bit of a meme, if that is all right. So here is what the public think we do as the ultrasound group. Now, we're actually in a physics department, and we do mostly engineering and applied physics. So the physics department thinks this is what we do, spend all of our time hitting things with hammers. So now we get on to what we actually do. We do hit things with hammers. There was, in fact, a whole project about it, and I'll say something about that in a little bit. But we do so many different things. We do things like trying to inspect aeroplanes, trying to work at high temperature to look at whether power plants are safe, looking at using ultrasound even to measure tiny little flows of water through pipes. Most of what we do is a thing called non-destructive testing. And this is all about finding problems that you can't see very easily. So things like railway tracks, trying to find cracking in those, or working with power plants, making sure that they are safe, that there aren't going to be any issues with them, keeping your aeroplane wings on. So all really important stuff that goes on in the background, and people really don't think very much about it until a disaster happens. We are trying to make new methods of inspecting structures that work a little bit better. So I'm going to tell you a bit about that, a couple of the things that we're working on, and have a look towards what the future might be. So in terms of what could go wrong, there are lots of different things that could happen. So metal is ductile, and that means that if it's subject to too many stresses, it could go pop. Generally, cracking will grow. And if you've got something which is a very corrosive environment, so in lots of these situations, like in power plants, you might have a lot of water. So you've got an environment which has got heat, you've got stress on your metal, and you've got the water there, which can lead to corrosion. And corrosive cracking is one of the most dangerous ones. We don't want this to happen at all, but it's going to happen, so we need to find things before it gets to be a problem. You might say, let's try and use better materials. So carbon fibre is a great one. It's got high strength to weight ratio, and it could be brilliant, except that it's very prone to damage. So things like if you drop your tools onto it, you can get impact damage. If you put bolts into it, then you get lots of stresses around where you're putting your bolts through. And again, this is damage. We need to find it and keep people safe. This is why we need to keep people safe, and it's probably the most serious part of my talk, because if we don't do this properly, we can have disasters. There was Hatfield, where there was part of the rail had broken. There was some knowledge that there was a problem, but no one knew quite how bad it was, and that led to loss of life. And when you look in places like America, you can have environmental disasters. If you have pipes carrying the oil and the gas around over the countryside, if there's damage in one of those and it breaks, environmental disaster. So we are trying to make sure these things don't happen. So how can we find defects? My great-grandfather had a job. His job was to wander along the railway tracks and hit them with a hammer. So I told you, the hammer was coming up here. He would wander along and he would hit them and listen. And he'd got such well-trained hearing that he could hear the difference between a piece of rail that was good and a piece of rail that had got problems in it. And he was paid to go and do that, walk around outside all the time. this isn't going to get you over the networks that we've got nowadays. We've got miles and miles and miles of track, so we need something a little bit better than that. So to think about how we could solve this problem, we can look to medical physics. And in medical physics, it's a lot easier because the human body is basically a bag of water. And so lots of the techniques that we could use to look through water will go through it really easily. One of the main ones that we think of is radiography, the X-rays, where you can take X-rays, you can put them through a human body and look for broken bones. We can do similar with metals, and this is our gold standard. So the gold standard, again, you take some X-rays, you send them through a piece of the structure. The size of the piece that you can do is limited by the resolution that you want, and it's quite dangerous because X-rays are not great things to be around, so you have to clear people out of the way in order to be able to do these measurements. And then you put a film behind the thing that you're looking at, and this means that you can then see any problems that might be inside your bit of metal. There are things that might be visual or electromagnetic techniques, so it's very easy to just look at something, and if there's a problem on the surface of it, you can see it, and then you know that's something that you've got to fix. In terms of electromagnetic techniques in medicine, we've got things like MRI. What we have is things like magnetic particle imaging. So this is where you have a piece of metal and you spray it with some liquid that's got little magnetic particles in, and then you apply a field. Now what that field does is it moves all these little particles around, and when we look at how the field travels through the piece of metal, when you've got a defect in there, the field lines go around the defect. And so all of the little particles like to gather together in that particular place. That's great, but it's really awkward because you have to clean the whole thing off afterwards, and it's not very kind to the environment, and you have to go and look at stuff, you have to apply different lights, and it's just basically a pain. So, ultrasound. I'm from the ultrasound group, so obviously I'm going to tell you ultrasound is the best way of doing this. It's not necessarily in every single situation, but it will give you a lot of really good information. So there's my little medical ultrasound, and here is someone doing an industrial ultrasound. They are doing a thing called thickness gauging. And it's a bit like if you were in a very echoey room or a cave and you shouted something into the cave and listened to echoes coming back. Has anyone done that? Lots of you have. Say nice things. There's some very guilty laughs just there. But the idea is the same. It's the same physics. We know that if we know the speed of sound and we measure how long it takes to get somewhere and back, we can work out how far it's travelled. It's the same if you're a bat. Bats use ultrasound to find their prey at night. They don't have the best of eyesight. They have some, which a lot of people aren't quite sure about, and they send sound waves out. They send out a little chirp. They listen for echoes coming back, and they can figure out with their echolocation where the moths are, and they can eat them. And it all comes down to this lovely equation. I have some equations in this talk because I'm a physicist. It's in the contract. I have to put one in legally. Otherwise, I will get back to physics and they'll probably give me the sack. So V is d over t. Speed is distance over time. Speed is distance divided by time. Very simple equation, but it explains all of the things that we do with ultrasound pretty much. So I'm going to show you just a little bit because I like getting distracted by stuff, and bats are cool. So I'm going to tell you about bats. In fact, actually, I'm going to tell you that moths are cool. Because bats like to catch moths and they like to eat them. There is one variety of moth which has learnt to do something clever, and it's learnt to send sound waves back at the bat. So it's a bit like if I was trying to throw a ball at you and get you to catch it, if I was then also shining a great big flashlight in your eyes in a darkened room, it would be really difficult to do that. So what these moths do is they send out the sound and it confuses the bats. So I've even got sound. That moth got. Most of them get eaten, but a few of them escape. I think it's the last one that does it. Yeah, it couldn't quite get the full grip on it. one escaped. But you can hear the sounds. This was really slowed down. They are making ultrasound, so very high frequencies, and sometimes these moths are able to escape. It's only one species, and someone's done some research where they put all the bats into this really small room and got them to try and catch moths for it, and that's where the videos are from. Anyway, what we do is we take a thing called a transducer. This is something which generates sound waves, so it turns energy from electrical energy into sound and then back again, and we can make sound and send it into a structure. So, oh dear, this structure has got a hole in it. We can't see it because it's inside, but we still need to find it. So what we can do is make our sound waves, and we can listen to how long it takes for the echoes to come back. So this little graph is just pointing out when we've got some echoes. So it's echoing once off the back, twice off the back, 3 times off the back. When we scan it along, make sound waves again, the sound waves are travelling a much shorter distance, and so the sound waves get closer together. We've actually got a real live demo of this and making it sound like really exciting. We've got some ultrasound here to show you, and Dr. Joe Cragine is going to come and do the demo for me.
As Rachel said, what we're often looking for when we're doing ultrasonic inspection is what we call a time of flight measurement. So that's measuring the time it takes for our signal to travel through our material, bounce off, let's say, a hole or the back surface of it, and come back. And by analysing that length of time that it takes, we can tell the thickness of our material or the location of holes. And if we do that same kind of measurement across an area, like a large area on our piece of material, we can build a picture of what that hole or those defects might look like if we see a crack in a railhead or something. So what I've got here is a railway head, sort of. This is our analog, so this is a piece of plastic that basically we've cut some holes in. And I've also got an ultrasonic transducer and an oscilloscope, which is going to interpret our signal. So the transducer is generating some ultrasound. It's going to pass through our material. And there we go. And we should be able to see a signal on the screen here. Now, I'm just going to add some couplant gel onto our railway head. And if we place our transducer onto, it might be slightly difficult to see.
Come and give you a bit of shadow.
Thank you. There we go. So if we place our transducer I'm in the top right-hand corner of our material here, we can see that we've got a little trace. That shows that that's the echo of that ultrasound traveling through the material, bouncing off the back surface, and then being reflected and detected by a transducer. If we move it to the next position, we can see we've got a signal in exactly the same place. So we can say with some certainty that these two signals have traveled the same distance. If we go to the next one, oh no, our signal's now in a different place. It's much closer in time. It's the signal has traveled for a shorter length of time, which indicates to us that we've got something in between that back surface and our top surface that we're taking the measurement from. So this is an indicator here that we've got a hole somewhere in our material. And if we do that across every single point in that surface, we can start to build up a picture of what that looks like. So if I add another little square here to show this is the square that I've just scanned that we think we've got a hole in, we get this picture and we can see, we probably do this on a computer, but we'll build up a picture of what the inside of our material looks like. And if I've got this right, it should match. Brilliant.
Thank you very much. Now I'm just going to scan through until I get to the right place. So one of the things that we like thinking about is how to actually make this sound. So you might have seen Joe squirting on the gel couplant. Has anyone had an ultrasound scan before? Quite a few of you have. Do you remember that horrible sticky gel? It's really important. What that gel does is it fills in any of the air gaps between the transducer that's making the sound and your body. We have to do exactly the same thing, because whenever you've got an air gap, you get reflection. So the sound will hit it and it will reflect back into your transducer. If you want your sound to go into something, you have to try and match the acoustic impedance, which is how we describe how easy it is for the sound to go through. So we use gel. And gel and water, they're great couplants, but sometimes if you're doing industrial work, they're not quite the thing that you want to use. So we like to think about how to do this in a better way. With the gel couplant and these transducers that we were just using, they're made of a material which is called piezoelectric. And a piezoelectric material is something where if you apply some pressure to it and you change the shape, what happens is the atoms move about. And when the atoms move about, it changes the polarization inside the material. Effectively, if you keep squishing and stretching it, you get an electric voltage generated across it. And you can use that to measure your sound. That's what the oscilloscope was showing. You can also do the inverse, so you can take an electric voltage that is an oscillating AC voltage and apply it to your material, and it will oscillate, and then you can couple the sound into the body. That is great. And that is actually what most people use. So the people who do the thickness gauging, so measuring how thick something is, that's a great way of finding out if there's problems hidden in the back of the structure, like some corrosion. If you've ever been on a train on a Sunday when it's going really, really slowly, they're probably doing some testing of the railway tracks as well. And we work with some people who use robots, and they send robots with ultrasound transducers all over giant structures to try and look again for problems. The difficulty, though, is this couplant. You have to have a way of getting the couplant to whatever you're looking at, and that can cause some problems. Sometimes they don't want you to come in and put couplant all over pieces of industrial equipment or railway tracks, for that matter, because it can slow down the braking somewhat. So on trains, they do it differently. They have a thing called a wheel probe. And there they've got their transducer sat inside this little wheel that's got like rubber on the outside, and it's full of liquid. And that helps the sound to transmit into the rails. The difficulty, though, is with this idea. Send out sound waves, listen for echoes. You've got a few issues. It limits the speed. So this is why people are always being delayed when we're doing the railway testing. Because although sound travels really quickly, it's still a finite amount of time for it to go into your rail and come back from a defect, so you can't go too quickly. It can also miss some of the problems. So it might have a little shadow region like is shown just here, where a little defect is shadowing the sound from getting to the end of the big problem there. And again, couplant is a problem on the railway tracks. Some of the things we want to do might be at high temperatures. So we might want to help the UK steel industry and make sure that they can make very high quality steel products by testing while they're casting them. That would be a really great thing to do. Alternatively, we might want to go to a power station and try and test it before they've shut everything down. Then it is at a very high temperature. But the issue is, if you need liquid couplant, that's going to boil off. You're starting to see the problem here. This stuff works brilliantly well, but it's awkward. So how might we do things differently? And this is where we get more into research and trying to think about how could we solve this problem by taking away the couplant. Is there a way of generating sound in a different way? And we're from a university, so we're allowed to think about things like this. We don't have to have a product that gets ready straight away. We use electricity and magnetism. So I've got my little electromagnet here. It's very impressive, isn't it? It's a screwdriver with some wire wrapped around it. And the screwdriver is very slightly magnetic, but not very. It's not very good at picking things up. If I was to take a magnet, this is going to be where I throw things all over the floor. I'm going to connect the magnet up to the wire around the screwdriver. I've now got an electromagnet. I've got current flowing through. And I've got a really good electromagnet. I think it can hold 4, almost. I'm just trying to show off now. Or maybe I'm just playing, because that's all science is, really. It's lots of fun toys, and the toys get better and bigger the further through you get. And then you get back to playing with screwdrivers and pieces of wire wrapped around them. Anyway, I brought that because it's fun, and because I like doing demos, but what I really wanted to talk about was this way of using electricity and magnetism to make sound. And we use things called electromagnetic acoustic transducers, EMATs. They are essentially a really complicated thing. They're a magnet with some wire wrapped around it. Really complicated or really simple. Now what happens is you take that piece of wire and you pulse the current through it. So you turn your current on and then you turn it off a few times. And we've got another equation. They'll be really happy with me in the physics department when they see this and they see I've got 2 equations in it. Don't think there's any more. It's a thing called the Lorentz force, and I've done lots and lots and lots of different types of research. The Lorentz force has followed me through everything that I've done, whether it's this industrial work, whether it's working with superconductors, whether it's working with magnets, it's always there. But it's brilliant. It says that if you have got a charged particle moving in a magnetic field, there's a force on it. That is all. So we have got charged particles, our electrons moving through our coil of wire. If we put that next to a piece of metal, the electrons, the electricity through the coil of wire is generating a magnetic field, and that magnetic field will generate a current in the metal. Some people just go this far and they will use the current in the metal and look at how that travels around all of the defects. We then apply a great big magnet and we look at the force. And the force is the charge times the velocity times the magnetic field. And that force acts on all of those electrons in the current, moves them around, and then they kind of drag the ions behind. So you've got, effectively, you turn your piece of metal into your loudspeaker for ultrasound. It's not very efficient. In fact, it's really, really, really inefficient, but it doesn't need couplant, and you don't have to be touching your sample. You just have to be within a millimetre or so. So it's not really that practical, but, you know, hey, it's fun, it's research, and we're in a physics department, so we don't have to get everything working straight away. But it's got advantages. The main thing is we got rid of the couplant. The next thing is we can do high temperature work, because for a start, you don't have the couplant, so you're not worrying about that boiling off. The next thing is we start looking at the components. Now, magnets are interesting. If you take a magnet and you magnetize it, and then you heat it up, if you get it too hot, it stops being a magnet. So, if we can keep it cool, we can keep our transducers working. And we cool it down by using water flowing through the pipes that go around the coil. They keep it cold, and this is our friend Mark doing some inspection at about 500 degrees C at a power plant. So didn't have to cool everything down, and he was able to do some ultrasonic measurements. Again, because we're in a physics department, we can listen out for new materials and things that are being made. Some magnets have got a much higher temperature, this Curie temperature, at which they stop being magnetic. So if you can use one of those, you can do your inspection up to about 500 degrees or so without using water. EMATs are also extremely adaptable. So when you start thinking about the defect that you're looking for, quite a few of them are on the surface. Now, with a surface defect, we don't want to send sound into the structure and listen for echoes coming back. We want to do things in a more sensible way. So maybe we could send surface waves along. And this is a nice picture of a Rayleigh wave. If you keep watching it, it will slightly hypnotize you. Keep watching it. When you go away, this is the best lecture you have ever listened to in your lives. And I'll move that. They are very adaptable. We can make these surface waves, and it's all by designing forces, because the force depends on the current and it depends on your magnetic field. So if we make a coil, which is a nice line, and a magnetic field which just goes straight down, we've got a force which is along the surface. We could redesign it. We could make things like racetracks, which give us forces in 2 directions, and we can send waves in lots of different directions. We could make a piece of wire which is all curved and going backwards and forwards. Those are our forces, and that gives us a really nice frequency for our surface waves. Or we could do something really weird, which is where you take a coil and you have lots of different magnets pointing in different directions, so you can get a force which is alternating. That is making a really weird wave that does that and travels through your material. So they're very adaptable, they're quite fun, and you can make surface waves. Now, if you look where the little pointy finger is, that's where we might have put something into this model of sound waves travelling along a railway track. Did you see reflections? There's some reflections, and what gets transmitted underneath is a little bit reduced in amplitude. So when you have your sound waves travelling along a railway track, they spread all around the piece of the track, but they can still interact with defects. You can get reflections, you can get changes in transmission, and by measuring those sorts of things, we can measure exactly where the defect is. And there's a really interesting thing if you can scan your sample. So these are, I'm making sound waves. They're traveling from one transducer to another. I'm going to scan them along a little bit. And we've got our waves over on this side. And as we get closer to the defect, the waves start to interfere. When you are right on top of your defect, they constructively interfere. And we get this really big signal that looks like a fingerprint of where a problem is. So I'm sorry for the blurriness of this picture. It didn't come out very well. But what you can see here is a two-dimensional scan. There is a block of aluminium which has got some problems in it, and then there are two different scans of it. And as you can see changing, this is the X direction, that's the Y direction, and can you see these blobs just there? Those lines where the colour is a lot stronger. That is where the signal gets bigger, and we know exactly where the problem is from doing these scans. We could also do something a little bit cleverer, because actually it's really hard to find small problems. But we could focus sound waves by making our force curved. So this EMAT is made with a curved wire, and so the force is going inwards to a focal point. This is a video which was made by using lasers to measure where the sound waves are. There's a little bit coming out the back, and there is a little ball of focused sound coming out of the front that can go and interact with problems. So how we can scan things, we can take these transducers, scan them all over our structure, and find a problem. When it is in exactly the right point, we'll get a reflection. So when we detect something, when we detect a signal, we know that we found a problem. This is 6 different lengths of crack that we looked for. We did these scans, and you can probably see that the length of the thing is growing. Can everyone see the blobs getting bigger? That is by using sound that's focused down and looking for reflections. We could do the opposite. We could look at how sound gets transmitted through things. In this case, we're looking for a missing point. And again, you can see the bit that's missing, which is the sound being blocked, is getting bigger as our defects are getting bigger. But this is where I really want to go. Where is the future? We do a lot of work on developing these different types of transducers, trying to find new ways of using sound waves and making sound waves. But really, the interesting thing is, where could we go next? And the answer might be, all of these measurements have measured a thing called the wave field. They've all been looking at our structure and having a look at how the sound amplitude is changing as a function of position. And it would be really nice if we could do this instantly. Then we might be able to see all of these signatures of a problem and identify a crack or an issue straight away. The gold standard for doing this is using lasers. So the little video I showed you used a laser interferometer. And if we use lasers, we can scan point by point, and this measures exactly how much the surface of the sample is vibrating. So that is good, except these are incredibly expensive. They are lasers, so you've got all of the eye safety problems, and you have to scan point by point, and it can take ages. So maybe we need to look at something different. So this now is starting to think about what exactly is the future. And obviously, when scientists think about what the future is, we all think about this. This might be the future application of the non-destructive testing, as in, if you've got a starship, you want to make sure it doesn't explode, and you need to be sure that your hull has got integrity. Now, the person who was in charge of this on one of these spaceships was, anyone know Geordie? Enough of you do, that's good. If I'd shown this afternoon, I don't think anyone would have known about Geordie. Geordie LaForge was the chief engineer on the Starship Enterprise in the Next Generation. And he was the engineer, and he solved loads and loads and loads of problems. He was also blind, and when I was growing up, he was someone that I really admired because it just didn't stop him. No one was bothered about it, and it was just great seeing examples of different types of people on telly. One day, they're going to have the chief engineer being sensible height, short. One day. This was all going on when I was being laughed at because I couldn't reach high cupboards. Anyway, He had this thing called the VISOR, which was the visual instrument and sensory organ replacement. And I think they missed a trick, because if they could have made this see sound, he could have just looked at the spaceship, at all the hull, all the pipework, and just gone, that's where your problem is. And then they could have fixed it instantly. So I always get distracted, and I want to tell you more about the Geordie. Not this one, this one. This is the Geordie, the Joint Optical Reflective Device. Yeah. And it is a visor that's been designed for people who have very limited sight. Now, what it has is a very big camera, and it's got a screen inside. So if you've got a small amount of vision, you can look closely and it will magnify the thing that you're looking at so that you can actually read. And I think they named it the Geordie because that was the very good description of what it does. Absolutely nothing to do with Star Trek. Honest. The other way, if you don't have any vision, you can use ultrasound. And there are a range of smart canes now. I've got the pictures of the Ultra Cane and the WeWalk. They use ultrasound, so they've got a little ball at the bottom, which is generating sound waves, exactly the same thing as we do. It's sending sound waves out and looking for reflections coming back. They have some of the sound waves go low so that they can find trip hazards and large items like post boxes and things like that you don't want to go into. They've got some that go up so you can look for head height issues as well. The WeWalk even links into an app, and you don't have to see the app. It gives you directions, so you can have that linked in to your position, and it will tell you how to get to different places. And these are brilliant. But we thought, if you're using sound to see, could we flip it around and use sight to hear? Could we make something that was visual? The dream is, oh dear, here is our problem again. We've got a hole inside, we can't see it, but we know that hole is going to block sound from travelling through. So if we could take something to make sound waves and send those sound waves through, there's going to be some of them get blocked and can't get there. Now, if we could make a lovely film on the other side or a plate or something, we might measure that shadow. This is where we're starting to head. It may be a dead end, it may work beautifully. We don't know yet, that's research for you, but I'm going to show you what we've got working so far. We're using liquid crystals. And liquid crystals, people think of them as being in displays. So probably quite a few of you have got a liquid crystal screen at home. They work because they're very sensitive to external fields. So inside your liquid crystal display, there is a big set of liquid crystals. I'll tell you what they are in a minute. And they're all aligned. They're within 2 pieces of glass. And then you've got various different polarizers and my words have gone for the thing that makes the electric fields on it. There will be a word, there's something there. But you are using electrical fields to change the optical properties of these liquid crystals. They can also have their optical properties changed by using ultrasound or magnetism. And they change the optical properties. Now, a liquid crystal, I think this is my last equation. This is a really, really beautiful one that just says, what is the average ordering of the molecules inside your structure? If you've got something like a solid, it's highly ordered. Everything is aligned, pointing in the same direction, and you've got an order parameter of 1. If you've got a liquid, then inside your liquid, all of your molecules are pointing around randomly. They're flowing and moving, pointing in different directions. Your average order, your order parameter, is 0. Liquid crystals sit somewhere in the middle. They have some order, but they can also flow and move around. And this is what gives them these really interesting properties. There is a type of window. Has anyone come across the privacy windows that you switch by flicking a switch? This is liquid crystals. And it's a type of liquid crystal that goes from being milky to clear. This is what we started with. So it's called polymer dispersed liquid crystals. Essentially, you take little droplets of liquid crystal and you put them inside a polymer or a glue, and then you let it set. Now, the liquid crystal has got a refractive index. This will describe how the light gets through it. It's got NO when it's aligned, NE when not aligned. What you do is you very, very carefully choose the refractive index of your glue, of your polymer, so that it matches the liquid crystal when it's aligned. So, for example, if you have zero field, what you've got is a solid that's got lots of different bubbles in that have got a different refractive index, and the light will scatter off it like mad. It looks milky. As soon as you align everything, it goes clear because you've got the same refractive index all the way through your material. That's how the privacy windows are working. They are switched by applying an electric current. Now, to prove that you could do this with ultrasound, we decided that we would measure an ultrasonic drum. And it is a transducer. It's called a Flexural ultrasonic transducer. I'm making that sound like it's really an impressive thing. We bought some car parking sensors off of Amazon. They were only about 50p, well, a few quid. And these are things that vibrate. And they vibrate at about 40 kilohertz, and they make a kind of a drum mode resonance pattern. If you try and make them work at much higher frequencies, they will still resonate, but they resonate in lots of different shapes. So you get patterns where the front face of it is vibrating a bit like this, where you've got some rings. And we thought this is a really good test bed. If we can see this, we're seeing sound, and that shows some promise. So we took our little parking sensors and we covered them in a thin paint layer for contrast, because it turns out if you've got something which is kind of silver and you're looking at something on top of it that goes milky to clear, it's really, really hard. So we painted them with a UV curable layer, gel nail varnish, bright pink. We even got the UV curable thing for the gel nail varnish. It worked perfectly. We needed something that nothing was going to go into. And we looked at them by eye. Now, in your normal displays, you need polarizers, and that shows you the change in optical properties. This just goes from milky to clear. So, by using lasers, one of our students spent 8 hours scanning something that big. And when it was resonating at a particular frequency, he got this pattern. And it looks beautiful. It's got a huge amount of information in there. It's quantitative. It shows you exactly how something is vibrating. We slapped one of these transducers, these sensors that we were making on, switched it on, and within a few seconds, we got this picture. And you can see this has also got rings. What we were measuring was the highest amplitude displacements, and they mapped beautifully. So we tried to do something where we were sending sound waves through a piece of metal. This is a little block of aluminium, and we took an ultrasound transducer, just like Joe was using, moved it around, scanned it along the back, and we could see it clearing. This is direct observation and a little video. Can you see the sound clearing it? Yeah, we did quite well getting it around that bit, and then none of us are any good at using the couplant because we try and invent ways of not using it. So none of us are good at this type of scanning, but you can see where the sound is coming through. We got so super duper excited about this. We thought, this is brilliant. And we went and showed it to some industry people. And the reaction was very much, yeah, that's nice. Can you give us a bit more resolution? Could you make it in color? And yeah, that would have been lovely. So we had to go back and think about it a little bit more. And we thought about it, and then went, well, actually, sound is energy. What about if we could send it through some sort of absorbing layer? The absorbing layer would absorb all the sound waves, and the only thing that can happen is the energy can turn into heat. And we know about seeing heat because, has anyone played with a thermal imaging camera? Some have. You can see heat escaping from buildings, or you can see the heat coming out of your body. You can even use this to do some of the non-destructive testing. So there is a thing called thermography, where you can send some heat into a structure and look at how the heat dissipates. And where you've got a defect, the way that the heat dissipates changes. So there is thermography, and that's all really colourful, and that uses the thermal properties of everything that's going on. I had some words there. We thought, can we make something that will see ultrasound that's kind of thermal? Can we make some absorbing layers and a sensor and just see sound? There is a different type of liquid crystal. And I'm going to need my hand model because my hands are frozen. It's called thermochromic liquid crystals. I've got some here. Can you see it's changed colour? And that's because Sarah's got much warmer hands than I do, and she was prepared beautifully, thank you. This changes colour with temperature. So, what about if we made our sensors with that? This is a really interesting material. Rather than things moving around, we've got all of our molecules in a helix. So they're in something a bit like that, in a spiral. Now, as the temperature changes, I'm going to pop this down on the floor. As the temperature changes, the pitch changes, so it gets further apart or closer together, depending on the temperature. And the wavelength of light, which is reflected from these different layers of the molecule, depends on the pitch. So it changes colour as it changes temperature because the helix that all the molecules are making gets further apart and closer together. Plus, it's really cool. It changes colour, and, you know, who doesn't like stuff like that? So if we could make something with that, it would be fun. Give me an excuse to play with it. Essentially, what we've got is something making sound waves. We've got something to absorb it, and then a liquid crystal sheet on top so that we can see what's happening. This is a video which is hopefully going to play. You are seeing sound here. That's it working at one frequency, turning on, working at a different frequency, back on at the first frequency again, and then the second. This is real time, and this is what the laser interferometer would give us if we had a spare 8 hours for each of these patterns. But you are seeing the vibrations, and where we've got enough amplitude, enough intensity in our signal, you can see the heat being absorbed and your sensor changes colour. So I'm just going to see if I can play that one again, just because I loved the gasp then. That was really lovely, everyone being able to see sound. This is so simple because it's just playing with energies. So here are some pictures, because you never know when actually the videos aren't going to work. This was some pictures of the sensor working at different frequencies on the same little parking sensor and measuring how it was vibrating. So we not only went away and did colour, which was what we were asked to do. I think it's really pretty and rainbow. It's nice, isn't it? But have we got the dream? Now, obviously, this is research. We are at a very, very early stage of trying to see if these might be useful. There are a lot of different liquid crystals. There are a lot of different thermochromic liquid crystals. Some of them will work at very high temperatures. Some of them will work at low temperatures. Some of them will change colour over 5 degrees. Some of them will change colour over a couple of degrees. And we're working out which ones are going to be much more sensible to use for what applications. There are even ones that are built for novelty values. So if you've had a mug that changes colour or reveals a picture when you put your tea in it, it's liquid crystal. So there are things that you can paint on that you can buy from crafting shops, and we're in the process of testing lots of these. But have we got the dream? Could we make a film from it? Obviously we had to, because otherwise I wouldn't be building up to it, because that would be really embarrassing if the answer was no. We took that little aluminium block that I showed you a video of earlier on, and we drilled some holes into it. And the holes are in this pattern that you can see behind me. So it's making this little stepped pattern, and it's not really the world's most difficult thing to find, but you start simple. If we couldn't find something this big inside our structure, we would be stuffed trying to find anything tiny. So this is what we've started from. Now, again, the warning is, none of us are any good at doing scans with that type of transducer. We are just so unused to using the couplant. We took this out to an industrial show once, and someone just came along and they just moved it around and got beautiful results. And I think I just need to kidnap them, make them stay in my lab for about a week and just go, we're just going to video you doing stuff. That'll be it. What we did was we took that block, and we put some of these liquid crystal sensors on one side of it, and we pointed a camera at it. It was a really complex camera. It was on a very cheap mobile phone that one of the students had. So very complicated, but actually, if you can do measurements with that, you can do measurements with anything. And then we took one of these transducers, and we covered the back with gel, and we moved it backwards and forwards, a bit like Joe did in the demo, but without the lovely grids to show you where to put them. And I've got a video of it. It's a bit sped up. The other one was real time. This is it sped up. Can you see the shadow appearing? About there. There's a bit where the sound really isn't travelling through. And there's lots of bits where you can see the colour. There are some bits in there where it's just we're rubbish at doing this, but essentially you can see the shadow. You're seeing the sound travelling through this material and interacting with the defect. Now, to analyse this one, we've done some work on trying to analyse the pictures where we can get the temperature change, which is related to the intensity of the sound. So we can do a measurement of what's going on inside there. Here, what we did was we took every single pixel of the video and measured the maximum saturation. And that just said, when was it brightest? Because it's got a black background on our sensor. So if we measured where is it the brightest, what's the brightest value of it, gives you this picture here. So we have got the steps. We've got these little bits over here, which look, drawing them, I'm showing you what they should be, but hopefully you can all see that they match beautifully the holes that we put in. This bit over here, that is us being rubbish. And I think it's good to admit these sorts of things. I should have brought it along and seen if anyone was feeling really good at this and tested you all. That might have been fun. It's not as good as medical ultrasound, but going back to the start, we are bags full of water. Sound travels beautifully through water, and so it's really easy to do the medical ultrasound scans. And quite often, us with our little industrial applications, we're trying to copy what they're doing and do something that is about a quarter as good, because in metals, our sound scatters. But we can still see an image of what the ultrasound is doing and how it interacts with the defect. So it's not there yet, but it's research. And the research is showing us that this is probably quite a promising way of being able to do our inspection. Maybe in the future we're not all going to be Geordie LaForge and with our visors and looking at things, but if we could take an industrial problem and have a paint-on coating, send sound waves through every now and again and just take a picture with our mobile phone and say that's where the problem is, that might make things a little bit easier. Maybe it'll happen. That's research for you. So I just wanted to finish by acknowledging I've had a lot of help with putting these things together. We are a group that works together. The liquid crystals have been done by Martha. We've had Claire and Joe providing some of the EMAT data, and Oksana, who is brilliant at all of this and is my liquid crystal specialist. And obviously, baby photos, because everyone loves baby photos. Thank you very much.